Greetings, everybody. So in this video, we are taking a break from chaos and we are talking about observers. So adaptive observers, okay, I'm going to explain what this is, for nonlinear rectangular descriptor systems with IQC, which means incremental quadratic constraints. Big title, I'm going to explain everything little by little. Let's not be in a rush. So basically, we're presenting the results from a recent publication in a very good journal, International Journal of System Science. I'm going to put a link for this article in the description of the video. If you have access, you can actually download it and read it for yourself. It has a lot of linear algebra. So I'm going to give you the very basics in a non-technical matter because it requires a lot of reading to understand every aspect of the design. Okay, it's a paper made with some very good colleagues and very kind regards to my colleague Mahendra, who have been collaborating for many years into observers. So reduced order, which means that we can reduce the state of the observer. Adaptive observer, which means that some parameters in the system are unknown and we need to estimate them. Okay, for rectangular descriptor systems, you may have heard them from undergraduate or graduate studies, are systems that are called algebraic and differential, which means that they have differential equations, just like state space systems, but possibly also algebraic equations. So descriptor systems are also called generalized state space systems. If you're watching the video, I'm assuming you already know what a state space system is. So consider descriptor systems a generalization of state space systems, okay? And they are rectangular, so not square, which means that the number of differential equations and the number of variables is possibly not the same. So in state space systems, you may have a system that is 3 by 3, so 3 differential equations, 3 states. In a rectangular system, you may have 3 differential equations, but 4 states, for example. Okay, so they not the number of equations and the variables in the state space may not necessarily be identical. And then we have nonlinear, of course, systems, and they have incremental quadratic constraints. This term refers to the type of nonlinearity in the system. And basically, this type of nonlinearity is one of the most general ones in the literature. You may have heard of Lipschitz nonlinearity. This is an even bigger category. So first of all, observer. Okay, what the hell is an observer? Very classic topic. If you have a graduate course or undergraduate course on control systems and modern control systems, or maybe you have the book by Ogata or by Nice or by Chichong Chen about state space systems and modern control, you may have heard about state space systems and you may have heard about an observer. So what is an observer? Let's say we have a system here and the system is a black box. We know the system, its structure, but we don't know the states of the system. So for this system, the only information we have is possibly regarding the input of the system and some information from the output of the system. And the output is in general a linear or possibly non-linear combination of the states. Okay. So the observer is a secondary system. Basically, it is a set of differential equations. And the observer, what it does is take information from the input and the output of the system. And from this information, the observer manages, ideally, to estimate the internal states of the system. So although we don't know the internal states, the observer can estimate them. So what you see right here in this graph is basically an observer, which is the black curves. The red, green, and blue are the actual states of the system. And you see that prior to 70 seconds, because I haven't actually turned on the observer yet, it fails to estimate the states. You see that the blue and black, green and black, red and black curves are completely different. But at 70 seconds, when I turn the observer on, the black states fall exactly on the red, green, and blue curves. So we have estimation when we want it. Of course, this generally doesn't take 70 seconds. Just that in 70 seconds, I turn the observer on. Okay, so that's the role of the observer. Take information from the input and output and estimate the internal variables in the system, x1, x2, and so on. Okay. In the case of adaptive observer, we have another interesting case, which is a bit more difficult. Okay, so this is a general formulation that we use in the paper. After some, linear algebra, we end up here. So we have a descriptor system, rectangular, We have F1, which is the non-linearity in the system. So the system is in general is non-linear. And note this, we also have non-linearity in the output. So this is a much more difficult situation because when the output is non-linear, the design is a bit more difficult. Okay. And apart from the non-linearity, what do we have? We have this parameter theta right here, theta. In Greece it is called theta, in English it's called theta. And this parameter is not a variable in the system. It is not a state. Okay, it is just a parameter that we don't know its value. Okay. So we need to design an observer keeping in mind that we know the structure of the system, but one parameter value is unknown. So the observer must be designed in such a way that it estimates both the states and this unknown parameter theta. Okay. So this observer that estimates the states and the unknown parameter is called an adaptive observer. Okay. And in general, when we want to control a system that has some unknown parameters, this is called adaptive control. Okay, προσαρμοστικός in Greek. Okay. So here we have this structure where the theta parameter is also multiplied by a function f2, which in general can be a nonlinear function. And again, this function is present in the output as well. So the problem is pretty tough. We have nonlinearities, we have adaptive control here because we also don't know a parameter. The system is rectangular, we have nonlinearities in the output. So it's a very tough problem. So for this problem, we design a descriptor. Okay, don't worry about the details because you really need to read the paper in full to understand it. But let's see some general remarks here. The observer is the actual set of functions and states that you see right here. So it's a differential equation. One important thing here. The system is a descriptor system, but the observer itself is not a descriptor system. The observer is a regular system, a classic state space. This is very, very nice because it makes observer design much easier. Okay, so this is very good result that we have a regular observer for a descriptor system. Okay, and this is not always possible, of course. Also, the state of the observer is z. That's why you see z dot here, the derivative, which means that this is the state of the states of the observer. But the actual estimation is not from the state of the observer, it's from he hat right here, which is a linear combination of the state of the observer and the output of the system. Okay, so he hat is what estimates the state he of the system. And apart from that, as I told you, we have an unknown parameter theta, so we need an estimation for this parameter as well. So the observer here is accompanied by another differential equation. You see theta hat here, okay, which estimates the unknown parameter of the system. By the way, for this unknown parameter, we generally don't know anything about it, but which is very common, we assume that we may know some upper bound, okay, and also we assume, which makes observer design much easier, okay, it's a very common assumption, we assume that this parameter is piecewise constant. This is very helpful for observer design because if the parameter is piecewise constant, its derivative is zero, okay. Now, in order for this observer to work, what do we need? First of all, we need a general algebraic condition, the first equation that you see right here. I hope I'm not blocking it. Okay, this equation right here. This is a very standard assumption. It's an algebraic condition. It's pretty much present in all observer papers. A variation of this will appear from paper to paper. Okay, so very standard assumption. The second assumption has to do with what type of nonlinearities do we have in the system. Because in order to design the observer, we need to somehow define a bound for the nonlinearities. Here, for F1 and F2, which I call it F capital here, we assume that they belong to the case of incremental quadratic constraints. They satisfy this condition right here. As you see, incremental quadratic constraints is a very general case of nonlinearities. You might have heard of the Lipschitz condition, the Lipschitz nonlinearity. Well, the IQC that you see right here is actually a generalization of it. Okay, so it encompasses other types of nonlinearities, and this is a very good thing because the observer works for many different types of functions. Okay, so this is a good result. Now, due to the presence of the adaptive term, in order for the observer to work, we need some assumptions. Unfortunately, these assumptions are pretty strict. So we have two algebraic, I hope you can see them, I'm not blocking them. These are two algebraic conditions right here that involve the matrices of the observer. Okay. The problem here is that in order to have the observer work, we need some algebraic constraints. Okay. Unfortunately, in practice, it is a bit tough to get these algebraic constraints to be satisfied. But it is common in all of the adaptive observer papers. All of them have some algebraic conditions that need to be satisfied in order to have a proper observer design. So why is it so? Let me explain. Without giving you too many technicalities. How does this observer work? How do we make the observer feasible? Well, any paper that you read on observer design is going to have pretty much the same type of designs. Okay, so if you download any paper on observer design, either in descriptor systems or in classic state space systems, the design is pretty much the same. Of course, the small details inside the design vary, but the general outline remains the same. So how do we design the observer? We start by considering, okay, the error, I'm sorry, between the state of the system and the estimates. So he minus he hat. Since this is an adaptive observer, we also consider the error for the estimate for the unknown parameter. So we have theta minus theta hat. Okay, this is the first step. We do compute these errors. Then what we do is we differentiate, so we take the derivative of this error dynamics. And here is where these conditions play such a big role, because when we take the derivative of these error dynamics, these algebraic conditions help us perform a lot of simplifications. So when differentiating the error dynamics, and especially later that we take the candidate Lyapunov function, we may end up with many terms inside the differentiation. The algebraic conditions allow us to discard some cross terms that appear. And when I say cross terms, I mean terms that involve the error of the state and the error of the parameter. So epsilon x and epsilon theta, some cross terms will appear that involve both of these terms. We can cross them out, delete them because we have the algebraic conditions being satisfied. Okay, so after we differentiate the error dynamics and maybe do some simplifications, you consider a candidate Lyapunov function. This is very standard in practice. It's a quadratic Lyapunov function. And what we do, of course, the function involves inside the error for the state and for the parameter as well. We differentiate this candidate Lyapunov function. And again, here, as we differentiate, we make a lot of simplifications where these algebraic conditions are very helpful. Okay. And the goal here is that we differentiate the Lyapunov function and try to show that the derivative of the Lyapunov function is negative definite. If we show that, we know from Lyapunov stability theory, it requires some additional steps in between, but I'm not going to give you the details. But the gist is that if this is satisfied, then the error dynamics eventually converge to zero. When the error converges to zero, basically this tells us that the estimate converges to the actual state of the system. Okay, and this holds both for the state estimate and for the parameter estimate. Okay, so in order to show that the derivative of the Lyapunov candidate function is negative definite, we end up with a condition that involves a linear matrix inequality, a so-called LMI. Okay, so considering these algebraic conditions and the conditions above, we end up with showing that in order for the observer to exist, a specific linear matrix inequality must be satisfied. Now, LMIs are not checked by hand. It's very difficult to check them. Okay, they involve very big matrices. But in MATLAB and in other languages as well, you can have the LMI toolbox, which basically very easily you can input to the MATLAB toolbox the matrices that are involved in the LMI, and the system solves it and gives you the result about whether or not the LMI is feasible. Okay. You can read, of course, the full proof inside the paper. Now, we couldn't resist including an example from chaos. So what do we have here? We have a chaotic system. Okay, if you know, of course, from the graph, this is the well-known Rosler system. In this system, what do we do? We have one unknown parameter, which is the theta variable that you see right here, theta times x2. So theta here is unknown. And not only that, we also have an unknown input u that you see right here, which is injected into the system. And just because in our observer design, we have the observer for a rectangular descriptor system, the way that the observer is designed allows us to estimate the states of the system, the unknown parameter theta, but also the unknown input u. Okay. So this is possible because we considered observer design for rectangular systems. Rectangular systems allow us to formulate this example in such a way so that we can estimate the unknown input as well. And this is what we do. You see the simulation results right here. So we estimate very nicely the states x1, x2, and x3. And we also estimate the unknown input, which is just a sinusoidal signal. So just in a couple of seconds, we have estimation of the unknown input. And we also estimate the unknown parameter theta. This takes a little bit more time. It takes around 20 seconds, but eventually we manage to estimate the unknown parameter, which is of course a constant parameter. Okay, this is an assumption for the observer design. So the observer works nicely. Here I have another example where I simulate the system and the observer again and again for different values of a gain factor, which affects how quickly we estimate the unknown parameter. So you can see right here that for different gain factors, the estimation can be from 20 seconds to 15, maybe up to, let's say, around 10 seconds or so. Okay. Of course, this requires a much bigger gain in value to be able to achieve this. Okay, but it is possible. So the observer works nicely. What can we do in the future? The results are very interesting, and I personally believe that you can have many different variations of the results, which of course can result in many different papers. So for me, one important and difficult problem is to possibly try and derive softer conditions for the convergence of the observer. Now, all adaptive observer papers have some sort of algebraic conditions that are required in order to have the observer design. Okay. Unfortunately, these conditions are a bit tough to satisfy in practice. So mathematically, the observer is obviously correct, but in practice, we saw that sometimes it is very difficult to find appropriate matrices that satisfy these algebraic conditions. So if possible, we can derive observer design with softer conditions. This is a very interesting problem. Another very interesting problem is to define and consider different types of non-linearities. IQC, incremental quadratic constraints, are very, very famous, and there are a very big family of non-linearities. So they include monotone, they include Lipschitz. Many kinds of non-linearities fall under the category of incremental quadratic constraints. But still, some other types of non-linearities don't fit the description. So you can define and design variations of this observer that fit other types of non-linearities. This is another possible paper. Then we can consider a whole different direction, which is to design other types of observers. So our observers here are basically what we should say are Leuenberger type of the observers. But there are other types, for example, functional observers that are very famous at the moment, very state of the art. I think you can possibly design observers for the same problem, but of different type, functional observers. Okay. And then possibly extend this design to fractional order systems. I don't have much experience in fractional order systems. Again, it would involve linear algebra, a lot of linear algebra. It is possible if you are interested in doing so. And again, a variation on the adaptive case, which is to consider the case that the system is a complete black box. So we don't even know the differential equations of the system, not just an unknown parameter, but the whole system is unknown. So here we would have to go with techniques like sparse identification, like the well-known Cindy approach. I'm not sure if we would be able to define a pure mathematical proof for this type of observer, but from a numerical perspective, it would be very interesting to see if it is possible to define an observer that doesn't know the system at all, that estimates the system, and then through this estimation manages to maybe estimate the internal states. I'm not sure how we would design that. This is very difficult, and I'm not sure if it's possible to define mathematical conditions for this. But from a numerical or a machine learning perspective, it is a very interesting problem. Okay, so many new works can be defined from this work. As I told you, I'm going to put a link for this paper in the description of the video. If you have any questions, write them down in the comment. Thank you for seeing this video and happy reading. Thank you very much.